The theory of stellar structure is one of the central frameworks in astrophysics, describing how stars are built, how they generate energy, and how they evolve over time. Stars may appear as simple points of light in the night sky, but inside they are dynamic spheres governed by a delicate balance of forces and physical processes. Understanding their structure reveals not only how stars shine, but also how they create the chemical elements that make planets and life possible. At its core, the theory explains that a star is held together by gravity, which pulls matter inward, while pressure generated by energy from nuclear fusion pushes outward. This balance, known as hydrostatic equilibrium, ensures that a star remains stable over most of its lifetime. If gravity were stronger, the star would collapse. If pressure dominated, it would expand uncontrollably. The harmony between these forces allows stars to shine steadily for billions of years. The energy source inside stars is nuclear fusion, a process where lighter elements combine to form heavier ones, releasing enormous amounts of energy. In stars like the Sun, hydrogen nuclei fuse into helium in the core, generating heat and light. This energy travels outward through the star by two primary mechanisms: radiation and convection. In the radiative zone, energy moves outward as photons slowly scatter through dense stellar material, a journey that can take thousands to millions of years. Beyond this lies the convective zone, where energy is carried more efficiently by the physical movement of hot plasma rising and cooler plasma sinking. The exact balance between radiation and convection depends on the star's mass and composition. A star's internal structure is often divided into three main layers: the core, where fusion occurs, the radiative or convective zones, where energy is transported, and the outer layers, including the photosphere, which emits the light we see. More massive stars have hotter cores that can fuse heavier elements like carbon and oxygen, eventually producing iron in the final stages of their lives. These processes explain how the elements essential to life, carbon, nitrogen, oxygen, and beyond, were forged in stars and later spread through supernova explosions. The theory of stellar structure is guided by four fundamental equations: hydrostatic equilibrium, balance of forces, energy generation, fusion rates, energy transport, radiation and convection, and mass conservation. Together, these equations allow astrophysicists to build detailed models of stars, predicting their temperatures, luminosities, lifespans, and evolutionary paths. Observations of stars across the galaxy consistently support these models, from the steady shine of main sequence stars like the Sun to the explosive deaths of supernovae. Stellar structure also explains the diversity of stars. Low-mass stars, such as red dwarfs, have long lifespans, burning hydrogen slowly for trillions of years. Medium-mass stars, like the Sun, eventually expand into red giants before shedding their outer layers and leaving behind white dwarfs. High-mass stars live shorter, more dramatic lives, ending in core collapse supernovae that can form neutron stars or black holes. The study of stellar structure has practical importance beyond astrophysics. It informs our understanding of the habitable zones around stars, the evolution of galaxies, and the chemical enrichment of the universe. By comparing theoretical models with data from telescopes and space observatories, scientists refine their knowledge of stellar interiors and the processes that govern them. Ultimately, the theory of stellar structure reveals that stars are not just distant lights, but engines of cosmic creation. They are the furnaces that power galaxies and the forges of the elements that build planets and life. By studying their inner workings, we gain insight not only into the nature of stars, but into our own origins as children of the cosmos.